Um, I think we're missing a few people up in Hattiesburg, but, well, that's our problem. Um, maybe they'll wander in later. Um, okay, now, today is the first of 4 consecutive class periods where we're going to learn, you guys are going to learn hopefully a ton about MATLAB. So we're going to be pretty exhaustive about it. Um, now, this is what I recommend. I see several of you up here, and yep, down there too, have laptops out and ready. So that's good. If not today, then I'd suggest it for next time. So as far as how this relates to the book, so I have, make this bigger, MATLAB tutorial, that's section 1.2, getting started with MATLAB, is pretty much what I'll be following and digressing as needed based on whatever questions I get. And also keep in mind, it's important to stay on schedule. Hopefully 4 class periods is plenty of time to plow through this whole thing. It is pretty lengthy. But if it seems like there are too many questions during class, maybe just defer some to after class or by email or whatever. But still, we have plenty of time to get things covered. Now, has anyone had any difficulty getting MATLAB?
I haven't been able to get my computers get shipped back to me for getting fixed. So
Oh, okay. So anyone who has their computer had difficulty getting MATLAB?
I'm trying to do it.
Oh, you are now? Okay. All right. Now, anyone up here or down at the coast continuing to have any textbook difficulties?
Where is it posted at?
Oh, okay. On the site, I believe I sent an email that had a link in it, but on the site, the class site, on the links page, you can get the first chapter there. So, supposedly this week the bookstore at the coast is should have enough for everybody down there. So, if we get to Thursday, and any of you down there still don't have it, let me know. Any difficulties getting a book up here in Hattiesburg? Yes? Oh, so the bookstore's out of them? Okay. Let's see. What about Amazon? Have you looked there yet? Or
I have some for $28 on
oh, okay.
It'll have to be returned on the 17th of December.
Okay. Or directly from publisher. Although Amazon's probably quicker. If we're coming to the end of chapter 1, which is in 2 weeks, and you still don't have it, at least get something ordered by then, and then I'll make sure that you're not without in the interim. Yeah. So, like on a chapter by chapter basis or something. So. Anyone else? Okay. Now, while I'm on the course site, actually, let me make this a little bigger or a lot bigger. What?
A lot more bigger.
Oh, bigger still?
Yes.
Really?
Yeah.
Okay. All right, now, this is the first assignment on MATLAB. So the 4 class periods devoted to MATLAB. Wait, let me make this whole window bigger. Okay. So September 12th, next Thursday, is when presumably we'll finish this tutorial. The next class after that is when homework is due. Now, quite a few problems. There are a grand total of 29. Some are really quick. Others not so much. but I want to point out that even though you have a lot of time from now, it's not an invitation to wait until like the 12th or 15th to get started. And the early problems, they're scattered throughout the section. As you can see here, like we're just a few pages in. Here's the first one. They're just all over the place through a section. So I would recommend that, for instance, whatever portion of this I cover today, you do the problems that are scattered within that part fairly soon, like in the next couple days or something. Get those out of the way. Don't let all 29 of them wait until like the 13th through the 17th. That's bad planning. I mean, we're almost a week into the semester. No one's behind yet, right? Well, certainly we can't be in this class inherently, but hopefully not in your other classes either. So plan to try to help keep it that way. Okay. Now, next thing, since I needed to make the web page bigger, I guess I have to make this bigger also. Okay. Although I also need to make sure that I don't have lines that are 20 characters long. So, let's see. Let's try this. Come on. Hello. Okay, it's thinking. It's still thinking. Come on. I didn't think a font change size would be this traumatic. Sorry, I did a font change size earlier and it did it pretty quickly, so not sure what the deal is. Okay. Okay. I think we broke MATLAB. All right. I'm going to restart it and see how that goes. Oh, I think it did it. Not over here, obviously, but okay. All right, so hopefully this is big enough for everyone. Could someone please turn lights off at the back? It's by the door. Okay, is that all right for everybody, including down there? I don't know if that affects anything, but okay. Okay. Although, what I can see up here is never matter because I have pages to look at, but we'll see how this goes. Okay. Now, so here when you launch MATLAB, the layout of a Windows might possibly be different because I may have messed with them since I installed it a very long time ago. This is actually not the one from a site license. Before we had a site license, I actually had to buy it, $500 because I'm not a student anymore. Oh well. Now, up here, very important. Unfortunately, the font size does not apply to this. This shows whatever folder or directory you are currently in. So by default, it may say something like users, Lambert's documents, MATLAB. Whether it'd probably be something similar whether you're on Windows or a Mac. And then I've created a subdirectory under that, like Math460 and then tutorial 19. And everything I do is going to center around this folder that I'm in. So for instance, if I create a file, it assumes it's going to be in that folder. So it's very important to pay attention to what folder MATLAB thinks you're in at the current time. Like for instance, suppose suppose I send you a MATLAB file, which we'll get into later in this tutorial, and you get in your email, and then or maybe you download it from my site, and you save it wherever your email program or browser typically saves things, which would be in a different folder. So you have to remember to, once you have it saved, to move it to whatever directory is here. So a lot of times when a student is running something and MATLAB complains a certain file can't be found, it's looking somewhere else than you think it is. Or maybe you put the file in the wrong place. So I just want to emphasize from the get-go, pay attention to that. Okay, what we have here, this window, the command window, that's where I'll be typing a great many commands. The commands that I've been using will be shown over here. Like as I do new commands, you'll see them appear at the bottom of this list. And like these are ones that I was doing earlier, although we can't see very much because of it being cut off. Over here are all the files that I currently have in this directory. We'll be looking at those later. And notice the extension .m. So files that contain MATLAB code have a .m extension. And then down here, workspace, as I create variables, they'll show up in here with some description of them. Well, we don't have any yet, but we will shortly. All right. Later, when we start looking at these files, there'll be a separate editor window that'll pop up. For some of you, it might be like docked in here, but I like to have it in a separate window because clutter. So it has its own default text editor, which has some features that are convenient for working with MATLAB code. You can use any text editor, technically, to edit M files, and you can have all your MATLAB operations powered by Microsoft Notepad for all I care. But the MATLAB editor is certainly the most convenient for working with that. Okay, now the very first command I'm going to acquaint you with is the one that's showing up here, the diary command. Diary command, what it does is everything I type in this window will be logged in a file. So then I can look at it later. What I'll do is after class I will post each one of these. So we'll have a transcript of what happens in this tutorial. Now, if I could use the command diary by itself, I could hit enter right now. And it'll create a file over here that's just called diary, and it'll put everything I type, or all of its output also that it generates will also go in this file. But I'm not going to do that because it's best for file names to have appropriate extensions. If I have a file that's just called diary with no extension, and I click on it, like in my Finder or Windows Explorer, your computer's going to be like, I don't know what to do with this. So I'm going to give an argument or parameter, a file name where I give it a .txt extension. So that way, if I want to open this later, like in Notepad on Windows or TextEdit on a Mac, it'll know what to do with it. It knows it's an ordinary text file. Actually, I'm going to put the date in here also. Okay, since we're going to have I'm going to have 4 tutorial files, one for each day that I'm doing this. So I go ahead and hit enter. So this double greater than sign, that is the MATLAB prompt. So for now, we'll be doing commands at the prompt. Later, we'll be putting commands in files. But at least now, we see down here, the tutorial file has been created, so whatever I type is going to go in there. Now here, notice the % sign. As soon as I type that, the text turned green. Percent sign indicates that the rest of the line is a comment and therefore will not be processed. So that's useful for documenting what you're doing, which is very important to do. Bless you. So when finished, if I want to stop logging, and this is something I will do today at the end of class, you just type diary off. And what that will do is it will close the file, stop logging. So at least it's good to actually close it so that these things are cleaner with file operations. So diary and an optional file name to start logging, diary off to stop. Okay. And yeah, so MATLAB has nice syntax coloring to indicate what is what. Okay. Next, before we get into doing anything mathematical, certainly want to be able to get help. And there's a nice command for that called help. If you just type help by itself, what you see are a zillion categories of commands that MATLAB has. And you can type help on each one of these to get help on that category, like help on elementary math functions or general purpose commands, file input and output. So you can click on one of these categories to get help on that. Or, for instance, if I type help ops, ops refers to operators and special characters. So if I do help ops, which is the same effect as if I clicked on it up above. So help ops lists various commands of the operations that you have. Now you can use plus, minus, asterisk, and you will to perform mathematical operations. But there's also functions that do these same things, and we'll see more about functions later. All the operators for comparing. They're testing for equality or less than, greater than, or logical operations like and or that you see in other programming languages. Special characters that have meanings like semicolons or quotes. Most programming languages use quotes for string constants, maybe single or double quotes. For instance, in C and C++, they use single quotes for an individual character and double quotes for a string. MATLAB only uses single quotes for strings. Okay. So, for example, if I do help on a particular operation like help EQ, so this is the operator for testing for equality. So that's the actual operator you would use, the double equal sign, which has the same meaning as in several other languages like C++ or Java to test if two things are equal. But you can use the operator, which is generally most convenient, and sometimes there's a corresponding function you can use instead. Okay, so you can have help in general, help on categories of commands, help on individual commands. And if you click on like reference page, I'll go ahead and do that here. But that would give even further documentation. So there's a ton of info available. It gives examples on how to use them. Sometimes these pages also have examples. So anything you want to know is here. Maybe it's too much and overwhelming, but they're not leaving you high and dry either. Okay. Now, MATLAB can be used as if it's a kind of desk calculator. I actually do not own a graphing calculator. I can't stand those things. So if I need to do something like I would do on a calculator, well, I might use one on my phone if I don't have my laptop handy. But for anything else, including graphing, and we'll see graphing later, I can use MATLAB. So what I'll do is a few mathematical expressions. So for instance, if I do a simple statement here, A equals 3 plus 4. So it performs the operation and stores the result. This is single equals. This is an assignment operation. It's assigning a computed value of 7 to the variable A. So it prints it out, saying that A equals 7, so you know what happened. And it's hard to see because it didn't change the font size. But over here in the workspace, we have variable A, and it indicates the value over here. So as I create more and more variables, you'll see this space fill up. Make sure as I go to stop me in case you have any questions. There'll be enough time for that.
I have a question.
Yes.
So is the value of 7 permanently attached to A unless changed in the future, or?
Yeah, it's gonna keep that value until you assign something else to A.
All right.
Yeah, and actually, this takes me to an important point as a contrast with what you may be used to from other programming languages. For example, in I should say like real languages like C++ or Java, you are required to declare variables to be of a certain type. Like if this was in C, I had to say that declare A as a double, for instance, a double precision floating point number, before, and then assign A to it. And MATLAB is not like that. You do not declare your variables to be a certain type. A represents a single, or I got a poor choice of words. A represents a double precision floating point number right now. But I could assign something else entirely different to A later. I could assign it to be a matrix, in which case, therefore, its type would change. I could assign it to be a character string. And MATLAB's like, okay, whatever you got to do. So that's important.
In the future, if I wanted to call A again, I just type A and press enter, or is there a certain?
Well, yeah, I can do that. For instance, if I type A now, if I did other things and I forgot what A's value is, I could do that to recall what its value is. Like if you don't see it over here, because once I create a lot of variables, this space would fill up. But yeah, it retains that value throughout this MATLAB session. So until I close MATLAB down, it'll have whatever is the last value you assign to it. At some point in this tutorial, I'll talk about saving values. So for instance, when you shut MATLAB down and then return to it. Okay, I'm going to create another. So standard mathematical functions are available in an intuitive way. For instance, square root or exponential or sine or cosine. All those MATLAB functions are available in MATLAB. So here's computing the square root of A. So now we have a second variable over here for B. Similarly, like I mentioned, the exponential. Okay. Now, notice it didn't really show up 7 because that's an integer. But once we got something that's not an integer, notice it displays 5 significant digits. That's the default. But if I do format long, and now I'll display C again, it shows 15 digits. So we have a choice of format. Internally, it's the same number. It's just how it displays it. Notice also the use of scientific notation. Once numbers get larger than like 1,000 or so, the scientific notation is the default display. You could do operations involving like multiplication of scalars. But it's now one thing to keep in mind, it is not smart enough to understand this. Suppose I do 2b. Now, if this was on paper, everybody here would know what that means, 2 times b. And often when students are taking something, a mathematical expression that's been written down or from a book, including mine, and coding that, it may have been written or in a book as like 2b, but you have to remember to actually put in the asterisk for multiplication. And notice sometimes when you put an invalid expression, MATLAB doesn't know what to do with it, it may try to figure it out for you, tries to figure out what you meant. So in this case, it guessed right. So MATLAB will try to help save you from yourself, but it can only do so much. Okay. Exponentiation. So now A is currently 7, but now I'm going to overwrite A. So exponentiation is done using up arrow, which is a logical choice, although not all languages use it. For instance, like Fortran and Python use a double asterisk for exponentiation, but not here. So notice A is 7 until I press enter. Oh, okay. Oh, that was a bad choice. I should have used C. But notice it's not exactly the same. Notice it changed from, because I said B is square root of A, so now I've undone that operation. But as we'll get to in chapter 2, there's some error in that operation. It's not exactly 7. It's a number slightly larger than 7, and that's what shows up here. So, in other words, the internal representation of A before as being exactly 7 is slightly different than the internal representation of A now because of the error involved in taking that value from the square root of A and then squaring it. So this is a good example of something that'll be a recurring theme, rounding error from arithmetic operations. Okay. So questions so far? All right. Apologies for boring anyone who already has MATLAB familiarity. Okay. Like those students who took 610 with me last semester, who ought to know all this already. Okay. Now, so far I've worked with variables that are only numbers, but MATLAB, MATLAB is, the name is short for Matrix Laboratory. It was designed for ease of working with matrices. In fact, the way MATLAB originated was back in the 80s when. So my advisor at Stanford, Gene Golub, who was the leading figure in numerical linear algebra, he taught a numerical linear algebra course of working with performing matrix algebra every year. But one year he was on sabbatical, so the course was taught by Cleve Moeller, who was a professor at that time. I don't remember where he was professor at, and so he wanted to create some software that would make it easy for students to get a hands-on experience of all the matrix manipulations that were being covered in class. So he developed what would eventually become MATLAB for that class. Then later he helped found the company, MathWorks. So he remains like their chief scientist or something. I know him personally from seeing him at conferences. He would visit Stanford quite often. And really, that's one thing that distinguishes MATLAB from other programming languages is the ease of working with vectors and matrices. And that's what I'm going to illustrate right now. So what I'm going to do is I'm going to create a 2x2 matrix. Now, this is a convention that I use, or many people use, that should be aware of using uppercase letters to refer to matrices, and using lowercase to refer to numbers or vectors. And often for vectors, there should be some way of distinguishing them from numbers, like maybe using an arrow for a vector, or in the book I use bold letters to indicate vectors. Or some mathematicians who like to denote numbers and vectors exactly the same way and leave it up to the reader to figure it out from context. And I think that's mean. But so for a 2x2 matrix, now what I do is I type in the entries one row at a time. Rows are ended by a semicolon. So when I hit enter, this is what the matrix looks like. And I'm going to create another 2x2. Now, what you can do, and actually I would recommend this, here I've separated the rows, the entries in each row by a comma. I'm still using a semicolon to mark the end of a row. So these notations are equivalent. I recommend using the comma because sometimes you may have more complicated expressions for your entries than just the numbers I've typed here. And if you're not careful, if these are complex expressions, it might be ambiguous. So if you use a comma, MATLAB understands very clearly, oh, this is where one entry ends and the next one begins. So up to you. Okay, so now what I can do is perform matrix arithmetic. So I can just do A plus B. And, okay, I'm scrolling so you can, well, I'm trying to make this a little bigger. So you can see what happened. Now, matrix addition is relatively straightforward. You're just adding corresponding entries. So the 1 entry, 1 and the 5 give you 6, 0 plus 7 is 7, 0 plus 9 is 9, etc. But I want to point out something unusual that happened here that hasn't happened before in this tutorial, because I did not assign A plus B to anything. I just said A plus B. And what happens in that case is, since I'm not assigning the result of this operation to a named variable, it gives it a name called ANS, short for answer. So the ANS is a special variable, so you should not try to define it yourself. MATLAB assigns any value to it that is not already being assigned to something goes into ANS. And we see it over here in the list of variables. Notice for matrices, sorry that the font is small, but for small matrices at least, it actually shows the entries. But if it's something large, it'll just show the dimensions. So ANS will hold on to this value until I do something else that doesn't make an assignment. So if I do some other operation that is not assigned to anything, that will overwrite ANS. So I could use this as a variable in another expression, and sometimes, actually fairly often I've done that. But you have to be very careful when using it. So for example, I can do this, 2 times ANS, and it doubles all the entries. So I'm able to recall this value of ANS to perform an operation and get what you'd expect. But notice, ANS has changed now. So this matrix right here, gone, poof, obliterated. So, and sometimes I'm doing several operations and I'm too lazy to save it into a variable, and then I realize, oh wait, I overwrote ANS. So, I mean, it can be convenient, but be careful. Okay. So what I'm going to do now is I still want A plus B. So now I'm going to assign it to another matrix C. So, and A and B never lost their value, so I have this matrix back again. I can multiply matrices by scalars. So 4 times A does what you'd expect. So it multiplies all the entries by 4. You can do all the usual matrix operations like subtraction. I can do matrix multiplication. Now, a thing to keep in mind, this is matrix multiplication like you learned in, for instance, Math 326, our linear algebra course. So there's also a way to multiply matrices entry by entry. That would be A dot star B. Now we don't have A and B on the screen here except in small font over here. But so this multiplies just corresponding entries, kind of like adding. But actual matrix multiplication is carried out using the asterisk. And therefore it has to follow the laws of matrix multiplication. For example, matrices can only be multiplied if they have a certain dimension. Can anyone remember what kinds of matrices you're allowed to multiply? What condition do their dimensions have to satisfy? I'm sorry. Yes, number of columns of a first has to match the number of rows of a second. So if you try something else here in MATLAB, it'll give you an error. So in fact, I'll illustrate that. I'm going to create a vector with 3 entries, 4, 5, 6. So here, to create a column vector, I can separate each entry of the numbers by semicolons, and that's a column vector. Whereas if I had left them out, it would give me a row vector. Okay, so now A is a 2 by 2 matrix. So I multiply A and W, that's an error. And so this error message, inner matrix dimensions must agree. That's exactly what we were talking about the columns of a first equaling the rows of a second. So whenever you see this message, you know that you tried to multiply things that were not meant to be multiplied. Okay. Questions at this point? We won't be doing too much of matrices in 460. 461, they really become front and center, but they'll pop up from time to time, just for convenience, if nothing else, for storage. Now, here's a command called, there's who that lists all of your variables, just the names. Actually, there are other commands. What lists the files in this folder. Do we have a where? Oh, you have to pay for where. Okay. Do we have when? Okay, we don't have when. We don't have how. We do have why. Why generates a random excuse. So if I keep typing why, okay, yeah. So there you go. So when you get really, really frustrated, this will frustrate you even more. Okay. But the command I really wanted to talk about was a variation of who. If I tack on an S, whose, it gives me more information about my variables. So, like, these are all the matrices, A, B, and C. So it shows that they're 2 by 2. And is also a matrix from a prior operation. W is a vector, so 3 by 1, 3 elements. Class is double. These are everything I've created so far is a double precision floating point number. And I want to mention the storage. So it's 8 bytes per number, because that's a double precision floating point number occupies 8 bytes in memory. So here I have a 2 by 2 matrix of 4 entries, so it occupies 32 bytes. So you get an idea of how much storage you've taken up so far. Certainly not very much yet. Okay. Now, okay. And we even have ands in here. That's on the list, but that's certainly subject to change depending on what operations you perform. Okay. That was weird. I make use of ands here, and I don't even discuss it until later in the book. So that's a book flaw. But oh well. All right. Well, that's what second editions are for. Oh, I'm not going to be like a calculus book and put out a second edition of this book. That's a trivial modification of a first. There are way too many mistakes for that. Okay. Now, I'm going to look at a different kind of entity than a double precision floating point number. Complex numbers. Okay. So I'm going to create a vector that I'll call Z that has two elements. So first is just 6. And then the other is a complex number, 3 plus 4i. So 4i is 4 is the imaginary part. So we need to use I to indicate the square root of minus 1. So the imaginary unit. So we can work with complex numbers quite easily in MATLAB. Okay. So now, was there a question?
Yeah, I was just going to mention about that. It appears that MATLAB takes to the variable I in multiplication a lot easier than it does something like A or B. Considering that you don't need anything like an asterisk on the I.
Yeah, so I guess I built that into the grammar as an exception, just because it's so intuitive for us to think of 3 plus 4i. And I'm not sure, it probably wasn't always like that, but actually, as long as I can remember, it has been. So, although what they recommend is that suppose I had 3 plus I. If that's my complex number, I could type 3 plus I. It's allowed, but it recommends 1i instead of I, even though they're the same. Presumably, it's more efficient. So I guess because I by itself, you can think it was ambiguous. MATLAB's wondering, is this a variable I or is it the imaginary unit I? Okay. So now, if I do whos again to see my variables, and we take a look at z. Z has 2 numbers in it, but now it occupies 32 instead of 16. Before it was 8 bytes per number, now it's 16. And it's marked as being complex. So why is it, why that much storage? Why did it double? Yeah, so real part and imaginary part both have to be stored. Now, what's one thing to keep in mind that's very important is the first number, 6, that was a real number. You still get charged in a way for that storage. It's still storing imaginary parts. So what that means is, if you have any vector or matrix or whatever, if even one element is a complex number, the whole thing is considered complex, stored as complex. Now, sometimes it can happen, for example, when using like a fast Fourier transform on real value data. The output of that is complex. Maybe you do something to it, and then you transform it back. Now, in exact arithmetic, the result may be real. But because of rounding error, you get these tiny imaginary parts. It could be in the order of like 10 to the minus 15. But now that storage is occupied by these trivial imaginary parts. So what you can do is if you have something like that, where there isn't, you want to toss out the imaginary part, what you can do is this. There are commands to extract the 2 parts. So real of z gives me the 2 real parts, 6 and 3. So, and then we also have imag for the imaginary part. So here, the first element was real, so the imaginary part is 0, and then we have imaginary part of 4 for the other one. And now, if I do whos again, y takes up half as much space as z, because if you extract the real or imaginary parts, those are considered real. So you get real number storage, half as much as complex. So when you're working with complex numbers, you have a quantity that mathematically is supposed to be real. Go ahead and take the real part, then you're not wasting so much storage. Now, if I go back to this command here, this is the first example in this tutorial of calling a function in MATLAB. A very simple one, just to take the imaginary part. But so imag is a function name, and then z is the input argument. And then y is called an output argument. So it's the result of a function. Functions can have as many input and output arguments as you like. We will discuss functions in more detail much later in the tutorial, probably not today. Actually, how far am I getting through this thing? Oh, okay. Still better keep cracking. All right. So So we'll see many more examples of functions. So z is the input, y is the output. So its function's job is to extract the imaginary part. So note that input arguments, they're enclosed in parentheses. So that indicates a function call, like in other languages, like C++, for instance. Okay. Alrighty. Now, okay, I'm going to point out what I just did here. Instead of hitting enter to go from this line to this, I didn't actually want to run that command because I already did it. I hit Control C. Control C is used to interrupt anything you're doing in MATLAB. Like if you have a long computation in process, and you realize you messed up and don't want it to continue, you can hit Control C and that will interrupt it. Here I just use Control C to not actually run this command, just bring me back to the prompt. Okay. Now, I've shown you how to create matrices in one way, just typing in the individual entries explicitly. But that's a 2x2 matrix. Can you imagine doing that with a 20x20? Oh, and that's a way that's a form of torture, I think. So what I'm going to show various other ways of creating matrices of any size that are particularly convenient. So I'm going to show several of these commands. Okay. So the first one is the ones command. The ones command creates a matrix where all the entries are equal to 1. And what you do, and here's another example of a function that has multiple arguments. In this case, 2. The first argument is the number of rows. The second argument is the number of columns in the matrix you want. So I go ahead and create that, and it gives me a matrix of 6 rows, 5 columns, all entries equal to 1. Now, so I don't have to type all that out. Now, if I want a square matrix, let's say I want a 3x3, I can certainly do 1s, 3, 3, but for convenience, suppose I do this, just specify 3 as the input argument. It will give me a 3x3 matrix. In other words, one input argument, it assumes you want that to apply to both the rows and columns. It assumes you want a square matrix. Okay. Now, suppose I didn't want that. Suppose what I really wanted was a vector of 1. Suppose I want a column vector that has, whoops, caps lock. If I want a column vector, so 3 1s stacked on top of each other vertically, like if I just wanted that, what would I put here? 3 what? Not 0. 1. Matrix of 3 rows and 1 column is a column vector. Whereas if I want a row vector, swap them. Okay. All right. So that's how you get a vector, which actually is contrast with Python, for instance. Specifying one dimension gives you a one-dimensional array. One could argue that's more intuitive, but okay. So that's how we create matrix of 1s. We can also have a zeros command. Very useful. It's actually even more useful, I think, than the 1s command. So it works the same way. Specify number of rows, number of columns. By default, one dimension is a square matrix. So here we have a 3x4 matrix of all zeros. Okay. All right. And then here's another rand. Creates a 3x2 matrix of randomly generated values. And if you're a probability nut, you're wondering how these are distributed. Between 0 and 1, not inclusive. Okay. So, and this is it comes in handy. Well, this leads to the concept of what's called a proof by MATLAB. So if you show that some result applies to a random case, so generated using RANDs, then surely it must be true in general. So that's a proof by MATLAB. Yes. Oh, sorry. What?
How do you typecast it to integer with just
Oh, so I could do this. Okay. Actually, I want to take this matrix Z. Well, first, notice the matrix Z. Okay, that's stored as a double, which is the default. Oh. I think it wants a size. Okay. So if I want 32-bit integers, I can... So you can cast it... So typecasting is done like this. There's a function representing the type, and you call that function. And if the cast makes sense, then it'll do it. So now, in 32, it's 32 bits or 4 bytes. So if I look at my variables again, capital Z, now it's indicated as 32-bit integers. And notice I have 12 elements occupying 48 bytes, so 4 bytes each. So I've saved some storage by casting those to int. On the other hand, if I take R, the matrix R, and so what did it do to get these numbers? Who can tell me? Yes, it rounded. So it does not truncate. It will round to the nearest integer. Chopping versus rounding, when we get to chapter 2, we'll talk more about that. And yeah, sure enough, the ones that are greater than 1/2 got rounded to 1, otherwise to 0. All right. Any questions? All right. Now, well, this is actually one of the homework problems, but I figured it would be fun to do it now. So you're welcome. All right. Well, 1 of 29, so you'll still be suffering plenty, so it's okay. Now, R has random values between 0 and 1. So using operations we've seen, how to get a 3x2 matrix the same size as R with random entries in this interval, -1 to 1, instead of 0 to 1. So, so if I have R with entries in 0 to 1, how can I perform straightforward matrix arithmetic operations on this matrix to get random entries that fall between -1 and 1? And I don't mean just like taking these, because these are already in that interval, but like an actual mapping from 0, 1 to -1 to 1. So really it's about a linear mapping from one interval to the other.
Can you make it an integer that is line at all?
No, we don't need that. So you can think of it kind of like a change of variable in a way. Kind of like maybe come up when working out integrals, like in Cal 2 or Cal 4, where you're doing a change of variable from one interval to another. So for one thing, you think about the widths of the intervals involved. 0 to 1 is a width 1. -1 to 1 is a width 2. So what does that imply about how you would transform one interval to the other? If that interval is stretching. So, my hearing is awful. Speak up. So, somebody said something I think might have been right. You are you are scaling. Scaling by what? Yeah. Okay. So if I take the interval 0 to 1 and scale by 2, what interval am I in now? 0 to 2. How do I get to what I want? Subtract 1. Scaling and shifting. So I do 2 times r minus 1. These values fall between minus 1 and 1. So these kind of operations, scaling and shifting, come in handy in a lot of situations. And I want to point out here, 2 times r, of course, is a matrix. But I'm subtracting a number. But MATLAB let me do it. So what MATLAB does in this case is if I am adding or subtracting a number from a matrix, it automatically takes this number and interprets it as a matrix of the appropriate size, and then subtracts matrices. So it took this 1 and made it to a 3 by 2 matrix of 1s, and then did the subtraction. So I want to make you aware of that also. Okay. All right. Questions about that? All right. It's one of those fundamental operations that comes up all the time, and probably should have been featured in more examples in classes along the way. Okay. All right. Now, okay. I'm going to create another vector here, a row vector, with the integers from 1 to 10. Okay. Now, imagine needing to create the same vector, except instead of going from 1 to 10, you're going from 1 to 1,000. You don't want to type that out. The functions I've shown you, ones or zeros, will not help you do this. But fortunately, something else MATLAB has will. Okay. So I'm going to do this instead. So this is an unusual construct in MATLAB. You don't see it in only some programming languages, but not very many. The colon operator. So I do 1 colon 10. That does the exact same thing. So 1 colon 10 indicates a range of numbers, starting from 1 up through 10, including 10. Okay. So if I want to do like 1 to 1,000, I could do 1 colon 1,000, and that would do the same thing. So this will come in very handy when we get to loops, for loops, for iteration. You'll see it come up there quite often, but in other situations too. Like you want to refer to several rows or columns of a matrix, a range of rows or columns. This is how you specify them. Now here's a variant on that. If I do 1 colon 2 colon 10, if I have 3 operands, the 2 in the middle indicates spacing. So I start from 1, then go in steps of 2 up until 10. Now, once I get to 9, if I take another step of 2, that would give me 11, which is out of bounds. So 10 is not included. So it will start here. It will not necessarily end here, but it won't go over.
Does MATLAB allow slicing?
Like
Like Python?
For getting like a cross section of a matrix. So yes, and we'll see examples of that later. Okay.
Are you able to do a 1 by 10 matrix the same way, like 1, 2,
If I want a column vector,
right? 2, 10.
well, colon generates a row vector, but then you transpose that, and the transpose we'll talk about a little later. I can go backwards. Bless you. This starts from 10, goes in steps of -2, and again, it will go as far as 1, but it won't necessarily hit it, but it won't go past it. And it's very important in this case when counting backwards, you want to have where you're still where you're starting from as your first argument. You might think, if I want to go from here to here, steps of -2 gives you nothing. So if I'm stepping backwards and my start is less than my end, you get nothing. Similarly, if I had 10:1, so if I'm stepping forwards, but my starting position is greater than my ending position, or starting value, ending value, you get nothing. And it's important that it work that way, because sometimes you really do want loops to run 0 times. That's part of the algorithm that you're implementing. So be careful about how you step backwards. Okay. All right. Okay. Now, there'll be a couple exercises on how to do variations of these. Although what you can do is do another example. The spacing does not have to be an integer. Suppose I do 1:0.1 10. Oh, I'm gonna go back to format short. Okay, actually, I'm gonna change the example. 0 to 1 in steps of 0.1. So it gives me 1/10, 2/10, 3/10, all the way up to 1. So you can use real numbers or non-integer real numbers for spacing. Okay. Now, next a note about output. Here's going to create a random 3x3 matrix. Now, as we've seen in every command I've done, after I perform an operation, the output of that, the result of that, is displayed. But sometimes you don't want that. Like if you have code implementing a complicated algorithm and it's generating output of every single intermediate result, that's a lot of output to sift through. Also looks kind of unprofessional. It may be useful when you're first trying to get something to work and you need to see how it's acting. So in the debugging stage, this can be desirable. But once it's working, and especially if it's code you want to share with someone else, you don't want to generate that cluttering output. So this is where a semicolon comes into play. So if I do this and I put a semicolon, it'll still generate a 3x3 matrix that I could print later, but it doesn't print it right away. So semicolon suppresses output. So this is a stark contrast with the use of a semicolon in other languages like C or C++, for instance, where a semicolon is required for termination of a statement. MATLAB is totally optional, but here's the effect. So it generates output if you leave it out, suppresses output if you put it in. Okay. Yeah, because you imagine like if it's a 3x3 matrix, so I generate a 50x50 random matrix and I have output going on forever. In fact, I'll do that now. I'll do 500. This is going to mess up my diary because this huge matrix is going to be in here, but yeah. Output for days. Well, and sometimes I've had much larger things in this, and yeah, it's awful. Because also, if this is format short, if it's format long, that would be quite a bit more. Okay. All right. Now, here's some more examples of building up matrices. So first I'll create a few matrices to use for examples. Okay. And I'm going to use a semicolon so it's not printing these, because it's what I do with them afterwards that matters. So A is 2x2, B is 2x3, 2 rows, 3 columns, and C is 3 rows, 2 columns. Okay, So what I can do is this. If I have A, B. Now, if these were numbers, it would put them right next to each other. But these are matrices. But it behaves the same way. It'll put these two matrices next to each other. So B is so A and B are stacked horizontally when I do this. So this part is A, the 2, 3, 1, 4, and this over here, the last three columns, that's B. So you can stack horizontally. You can also stack vertically. So A has it's 2 by 2, C is 3 by 2. So the result of that is going to be a 5 by 2 matrix. So here's A up here, the first two rows, and then down here is C. So that's how you can build larger matrices from smaller ones. It's very convenient. Okay. You can also create an empty matrix. I'm going to create an empty matrix right here, X, by just putting square brackets with nothing between them. Okay. So if I do now a helpful command in MATLAB is a size command. So size of X for a matrix will normally return the number of rows and number of columns, but there aren't any in this case, so it's a 0 by 0. So no storage has been allocated. But I can still stack. So if I want to tack on a 1, so now there's nothing and then 1, so now there's a 1. But now I can keep going. I can tack on a 2 now, and the vector is growing. I can tack on more numbers all at once. So now we have 3, 4, and 5. So you can grow vectors or matrices as long as you stack in the appropriate way. One of the homework problems deals with stacking inappropriately. So also very convenient. However, there's one problem with doing what I've shown you here. And that is, like here, I have a vector with 2 elements. Now I have a vector with 5 elements. What happened when I performed this statement is it took that vector of 2 elements, deallocated it from memory, then allocated a new vector that has 5 elements, space for 5 elements, to put the old one in there, and then these 3 new values. So every time I do this, and I'm growing a vector this way, it's deallocating and reallocating. And over time, that generates a lot of unnecessary overhead. Really slows your code down. Whereas if you know how many entries you're going to have in the end, you can pre-allocate using the zeros command. So if you know how much space something's going to occupy, go ahead and create it using the zeros command, however much space you're going to need, and then fill in as you go. How we will do that, like to refer to certain submatrices, is something that's coming up in this tutorial. When I've done that, like if I had to do this, conveniently but lazily, to keep reallocating, and then I go ahead and use pre-allocation using a zeros command, it really does make a noticeable difference in the speed of your code. So that's something to be aware of. Okay. And actually, yeah, this is a very important part to get to. How do we work with individual entries of a matrix? Okay. All right, I have my example A from before, same one. So I want to refer to an individual entry, like the entry in row 1, column 2. This is how I do it, using parentheses to indicate you're accessing an entry, and then the row index, column, or comma, then a column index. And that gives you the value 3. So, very important point. MATLAB uses one-based indexing, as opposed to languages like C, C++, Java, and Python that use zero-based indexing. And that creates some headaches sometimes, whatever indexing convention you use. Okay. Now, if you have a vector, you would just use one index, and it'll fetch that element of a vector. Whether it's a row or column vector, it'll understand what you mean. So more examples of referencing elements or portions of a matrix. I'm going to create a random 3x3 matrix here. So suppose I want the first row. So I can use row 1. Okay, so row 1, and I want the entire row. Well, this is a 3x3 matrix, so columns 1 through 3, that would do it. So that extracts the first row. But there's a shorthand. Suppose I do this, just a colon. That does the same thing. So colon by itself is so refers to all valid indices. So by putting in the second position here, I'm telling it to grab all columns. If I put it in the first position, that would refer to all rows. However many there are, so you don't have to keep track. It figures it out for you. Okay. I can use ranges for both rows and columns. Suppose I want the upper left 2x2 block. First 2 rows, first 2 columns. So that gets it for me. I want the so what I was illustrating earlier. This is the third column. So colon comma 3 refers to a column. I mentioned earlier 1 comma colon. That's the entire first row. Okay. Another convenience. Suppose you know that you want the last column, for example. Whatever that column may be. So I could do A colon end. So end is indicates last column. It's similar to Python using of a -1 index. Okay. I could do, for instance, suppose I want rows 2 to the bottom. Okay. But only the entries in the first column. Then that would be this. So rows 2 and 3, because it's a 3x3 matrix, just the entries from the first column. All right. Now, every example I've done is either a single index, like first column, or a range of consecutive indices. It's not required. I can pass any indices I like. They don't have to be consecutive. Suppose I want rows 1 and 3 in their entirety. I could do this. I create a row vector containing the elements 1 and 3. And then I want the entire row. So I use a colon to indicate all columns. So that gives me rows 1 followed by row 3. Okay. They don't even have to be in order. So suppose I want the entirety of column 3 and column 2. So if I list the 3 first, it'll give me column 3 followed by column 2. Okay. All right. Okay. One more example, I'm going to create a random 5x5 matrix. So now what I want is rows 1, 4, then 3, and then columns 5, then 2. So it's going to take column 5 and column 2 in that order, and then the first, fourth, then third rows. And that generates this 3 by 2 submatrix, 3 by 2 because I have 3 row indices, 2 column indices. For those of you familiar with Python, a contrast is that if you did something similar with the appropriate syntax, like this, as written, that will be an error. You have to take the, like first you'd have to take the appropriate rows, that matrix, and then take the columns of it. So it's 2 separate indexing expressions. Or if I had 2 vectors of indices here, like if I had like that, Python would give me a vector with B15, B42, B31. But MATLAB doing this would generate a 3 by 3 submatrix, taking the indicated rows and columns. There's a very different behavior in that case. If you're not familiar with Python, you can ignore what I said for the last minute or so. Okay. All right. Questions at this point? All right. Let's see how much I have. Just shy of 15 minutes. Okay, but like a little more than 10 minutes left. Okay, actually, we're getting close to a natural stopping point. We'll talk about the transpose, since that came up earlier, but it's also the next section in the tutorial. So, because it was asked earlier, like if I have a vector like this, 0 to 1, in steps of 1/10. So this would give me a row vector of 0, 0.1, 0.2, 0.3, etc., up to 0.9, and then 1. A row vector. But if I want a column vector, what's the easiest way to do that? The apostrophe or single quote is the transpose operator. So that would give me a column vector. So any expression that would be a matrix or vector of any kind, by putting the single quote after it, that would take the transpose. Except what I said is not entirely correct because of complex numbers. There's a slightly different behavior with complex numbers. So I'm going to make a complex vector like I had before. All right, so here's a row vector of complex numbers. Now I'm going to use this operator here. That is not the transpose. Can anyone tell me what happened?
Since it changed position in the matrix, right?
Well, it did make it into a column.
It turns the 2 to 1, so it's got to be negative.
Yes, that, a minus. The plus here became a minus here. That is, as I heard someone say, that is the conjugate, the complex conjugate. So, this single quote operator is not the transpose. It is called the Hermitian transpose. And what does that mean? That is transpose and complex conjugate. So suppose you have a complex vector like this z, and you really want the transpose. You don't want this conjugation junk. How would you do that? So a dot followed by the single quote, and that is regular transpose. Now for real valued vectors, matrices, doesn't matter, but for complex it does. So if I do z dot quote, then it's 3 plus 4i. All right, so that's one thing to be mindful of, and yes, I've been burned on that from time to time. Now, you might find that strange. Like, why would the simpler operator, just a plain old single quote by itself, perform transposing and complex conjugation? You'd think that the default behavior would just be plain old transpose, just changing rows to columns and vice versa. A reason why is that a lot of algorithms or results for real vectors and matrices, if you want to generalize them to the complex case, almost always what happens is if you had a transpose in your algorithm for the case of real valued vectors and matrices, the appropriate generalization is to use a Hermitian transpose. But if you just go for regular transpose, your result would not apply. So if complex entities, the Hermitian transpose is far more useful than the far more prevalent than the regular transpose. Okay. All right. So, questions about that? So if I just make an ordinary matrix here, like a random 3x3, bless you. Bless you. So if I use, in this case it's real, so it doesn't matter which one I use. So notice the diagonal entries stay the same, but notice like the 8368 and the 7728, that those flip. Okay. Now, so what that means is there are many cases where you want to test something out that you've done and you need a random matrix, so you can use rand. But what if you need the matrix to be random and symmetric? How would you do that? The symmetric part of a matrix. So if I take A plus A transpose over 2, a matrix like that, for any matrix A, if I take A plus A transpose over 2, that is guaranteed to be a symmetric matrix. In other words, it's equal to its own transpose. That's what it means to be symmetric. Intuitively, you see what it means that if you look across the diagonal, the entries are mirror images of each other. So any matrix that is equal to its own transpose is a symmetric matrix. Not sure if that was ever covered in classes like 326. Yeah, but those of you who are brave or foolish enough to go on to 461 will have a whole lot of linear algebra dropped on your head. Okay. So, questions at this point? We're getting close to the end. Okay. There's only 5 minutes left, and we've gone at for an hour and 25 minutes solid, so I'm going to stop here. But we'll have plenty more MATLAB tutorial. I'm going to do diary off to end the logging, and I will post that on the site later, probably tomorrow when I also post a video. So, scram.